Hi everyone, we'll get started now. Welcome to the fourth lecture of the Deep Reinforcement Learning series. Today we're covering our second deep algorithm, which is Deep Deterministic Policy Gradients, or DDPG. So what did we do last week? Well, last week we covered basically a series of transformations that get you from the value iteration algorithm into the DQN algorithm. And we tried to motivate each one of these transformations. We tried to see what problem there is with value iteration and how DQN solves this problem. So we first dealt with the fact that typically our state space and action space are very large. And so we can't just have a finite, we can't just have a representation of the value at every single state action point. Instead, we need a Q function which generalizes from a finite collection of points to all the other points that we haven't seen yet. We then introduced the done signal. The done signal is just a cheap trick that sets values of terminal states to 0. So there's really not much going on here. It just forces the values of all terminal states to 0, not very conceptually complicated. We then went from forming regression targets via expectations to forming regression targets via sampling experiences. And this transformation allowed us to move from a model-based algorithm where we need to know how all the possible transitions of a particular state action pair into a model-free algorithm where we can learn directly from experience in the environment. We then introduced the memory replay buffer, which allows us to gather experience from the environment, load this experience into the memory replay buffer, and then learn directly from experience that's relevant to the kinds of states that we visit, rather than being given a collection of experience to learn from. So this allows us to tailor the experience we're learning from to the kinds of problems that we currently face and the kinds of things that we need to learn at that point in time. We then introduced the fact that we should use a neural network as our learned Q function. Why is this? Because many domains involve unstructured data like images and text, and neural networks are just really good at this kind of thing. And lastly, second to last, we went from initializing a new neural network every time we wanted to train a Q function to just fine-tuning the same network continuously. And this means that we can make really efficient use of learning because we're sort of using all the previous learning we've done to start off with a good initialization for the next batch of learning. And lastly, we did this quick feedback loop where we quickly interleave training and acting. So today we're going to cover, basically we're going to cover DDPG, and the way we're going to do it is by considering differences with DQN. So this is going to be like a comparative study of DDPG versus DQN. So first we're going to cover network architecture, what's different between how the networks are set up. Then we're going to cover how the policies work. So in DQN, we had this epsilon greedy policy. In DDPG, we're going to have a different policy. Then we're going to cover how they differ in how value functions are trained. Then we're going to cover how DDPG trains its policy. Now, DQN doesn't have a policy, an explicit policy representation. It's induced by the value function, but DDPG does, and we're going to cover how you train this policy. And then we're going to cover how they update the target parameters. So we're just going to look at all the different parts of DQN and ask, like, how do I change these into DDPG, and why do I make those changes? And then I'll summarize the whole thing at the end. Okay, so to start the lecture, we're just going to recap DQN, just so we all have that fresh in our minds and all remember how DQN works. All right, so it begins, we're going to loop this whole thing, right? So this whole thing we're going to loop. So what happens in one loop? Well, we start by synchronizing the target network parameters. Remember, the function of the target network is to form regression targets. So it's going to be used for forming value estimates. It's going to be used for this bootstrapping. That's what the target network's for. So the first thing we do is synchronize the target network parameters. We then have 1,000, or again, these are concrete numbers, but these are hyperparameters. So the 1,000 here doesn't have to be 1,000. Could be many other numbers. This is one number that's of the right order of magnitude to give you an idea of what kind of number you should be expecting to see here. So for 1,000 fine-tuning steps, we're going to alternate interacting and fine-tuning. All right, we're going to alternate these two processes. In interaction, we're going to interact with the environment for 10 steps, again, just an order of magnitude, could be 5, could be 20, not really important. We're going to interact with the environment using the epsilon greedy policy with respect to our action value function. QSA phi here are the network parameters, right? Phi is our network parameters, QSA phi is a neural network parameterized by phi. What do I mean by the epsilon greedy policy here? So the epsilon greedy policy, the way this works is epsilon proportion of the time, I'm going to be randomly choosing an action. So epsilon would be something like 0.05, and 5% of the time I would be randomly choosing an action. What about the rest of the time? The rest of the time I act greedily with respect to Q. So that means that I look at all the Q values off the state that I'm in, all of the actions off the state I'm in, and I choose the one that has the highest action value estimate, right? And that's greedy action selection. So during this step, when I'm interacting with the environment, I'm using this epsilon greedy action selection so that I can most of the time perform actions I think are good, and they're going to get me into the part of state space that I need to explore. And then some of the time I'm going to be choosing random actions. The epsilon portion of the time I'll be choosing random actions, and this is going to explore different options off that state, right? So this is a way of trading off getting to the parts of state space where you need to explore and exploring those parts of state space. And then every one of these experiences that I have, every time I have an experience, which is going to be I was in a state, I did an action, so SA, I got a reward, R, I transitioned into a next state, S prime, and if that next state was terminal, then D is 1, so D is my done signal. If the next state was terminal, D is 1, otherwise D is going to be 0. So this is a transition, and I'm going to load each one of these transitions into the memory replay buffer, one by one. Then, after interacting with the environment 10 times, loading each transition into the memory replay buffer, I'm going to have a fine-tuning step. In the fine-tuning step, I'm going to sample a mini batch of transitions. So I'm subsampling from my memory replay buffer. My memory replay buffer, remember, has about 1 million transitions in it. And I'm going to subsample 32 of them. Just choose 32 transitions at random from that memory replay buffer. And then for each, this is going to be my mini batch. And I'm going to use these, in each one of these transitions, I'm going to form a regression target. And remember, my regression target comes from looking at the, it's like a 3-step transformation. I take the Bellman optimality equation, then I bootstrap by replacing the Q with my current target Q function, and then I remove the expectation and replace it for a sample. This is the transformation process that gets you these regression targets. Start with Bellman equation, then bootstrap, and then sample. And that's how you get the regression target. So that's where this came from. And remember, it's just saying the value of being in a state action pair, yi, can be estimated as what's the immediate reward I got, plus discount factor because it's 1 step away, what's the value of being in the next state that I end up in. And the 1 minus d here is just forcing that next state to 0, next state value to 0, if the next state is terminal, because all terminal states have value 0. And then I perform one update of my parameters phi by fine-tuning QSA on input-output pairs of state action inputs and regression target outputs using an L2 loss function. And then I'm going to just loop this whole thing. All right? Great. We'll just briefly pause, and if anyone has any questions, now's a good time to address them, I think. Okay. Yeah, does anyone have any questions about DQN? Otherwise, we'll go on. Okay, great. So, as I said, oh yeah, okay, so first of all, let's compare DDPG and DQN at a high level, so you know like what the fundamental differences are and what the fundamental similarities are. Okay, both of these algorithms are model-free. And remember, model-free means I don't need to either be given or to learn a model of the environment. Instead, all I need is to interact with the environment directly and learn from that experience that I'm getting. So both these algorithms are model-free. Neither of them use a model of the environment. Both of them are off-policy. And remember, a hallmark of an off-policy method is that it uses a memory replay buffer. So both of these are going to use a memory replay buffer. They're both going to have a big store somewhere, and they're going to load transitions into it, and then at some later point in time, subsample from that store to form mini batches that they're going to use for training, right? That's what we saw in DQN. That's how DQN does it. DDPG going to do very similar very similar kind of thing. So they're both off policy. They reuse previous transitions that occurred a long time ago so that they can be very sample efficient. They can squeeze a lot out of the data that they have. DQN is an action value method. And what do we mean by this? So DQN just learns a Q function. This is the only thing it's learning. It's going to learn a Q function, and then it's going to use that Q function to choose which actions to take. And this makes it an action value method. You learn a value function, and you use that to take actions or to decide which actions to take. So you are an action value method, right? So DQN is an action value method. DDPG is an actor critic method. What do we mean by an actor critic method? We mean that it learns a policy and it learns a value function. And the policy is the actor. It's the thing that's going to decide what actions we take in the environment. So it's the actor. And the value function is the critic, because the value function's job is going to be to provide a learning signal to the actor, right? So so there's like a fundamental difference. So these are similarities. This is a difference. DQN, the action value function, is sort of the fundamental thing you want to learn and what you're trying to use to do everything else. In DDPG, learning an action value function is a tool for training a good policy. It's a critic. It's not going to be choosing actions itself. It's going to be used to train a policy, and the policy is the thing that's important. Lastly, and this is another really important difference, DQN is only applicable to discrete action spaces. Now, why is that? It's because in DQN, we're taking a maximum over actions, and if there are infinitely many actions, I can't perform this maximum operation. More concretely, the DQN architecture is I shove in a state, and then I get a value estimate for each action off that state. And if there are infinitely many actions, I cannot make a neural network to do this. So I can only do this if there's finitely many actions. DDPG, on the other hand, is only applicable to continuous action spaces. So I have to have an action space that's continuous. I can't apply it to a discrete one. So this is why these two algorithms are sort of paired up like this in this lecture, because you can think of DDPG as sort of like DQN, but for continuous action spaces instead of discrete action spaces. So practically speaking, if you're asking which algorithm should I use, if you're in a continuous setting, DDPG. If you're in a discrete setting, DQN. There are many other algorithms to choose from, but if you only know these two, that's the criteria to use. All right, any questions at this point? Yep.
Is there any relationship between like the discrete versus continuous action space and the choice of an actor critic versus just a Q learning method? Is there, for example, like an actor critic version of DQN?
Yeah, you can formulate actor critic algorithms for discrete action spaces, yes. So A2C or advantage actor critic works for both continuous and discrete action spaces.
So these are kind of orthogonal choices.
Yeah, exactly. That's a really good way of putting it. These are orthogonal design choices. Great. Any other questions? No. Wonderful. Okay, so first things first, how do these two algorithms differ in the way they set up their neural network? So let's briefly recap the network architecture for DQN, which I went over last time, but quite quickly. So we're going to cover it in a bit more detail today. So for the network architecture for DQN, I'm going to have a state, and I'm going to shove this into my network. So I have a neural network body. So this is typically going to be something like an MLP, a multi-layer perceptron. It could be a convolutional neural network if you're dealing with Atari, for example, where your inputs, your states are Atari frames. You're going to be using a convolutional neural network. If you're dealing with something like language modeling, this might be a transformer, right? But it doesn't really matter. What matters is you have a neural network body that you're going to shove the state in. And it's going to be a neural network that's appropriate for the kinds of states you're seeing, right? And then off that body, you're going to have a readout head for each action. So these triangles here are linear maps that map to a single value. So this is a readout head that maps from the output of this body, which is here, the output of the body, to a single value, which is the value estimate for the first action of that state. And then I'm going to have another readout head for the second action off that state. And then another readout head for every single action off the state. So in this case, there are 6 actions off every state. And so I have one readout head from my neural network body for each one of these actions. And then when you train, you're training this whole thing. But more specifically, whenever you train, you're training a particular action value. So suppose I'm training the first action value, then I'm actually just going to look at this output and compare it to my regression target and train on that, right? So when I want to know a particular action value, I just pick the relevant head from the network, right? We briefly covered this last time, but to recap, there's a reason we compute all of these at the same time. And that reason is, so another way you could do things is put both S and A into the body and just get one output at the other end. Why don't we do that? Why do we do things this way? The reason we do things this way is because in DQN, typically whenever we're computing action values, we're comparing action values, right? So if I'm doing epsilon greedy action selection, I'm choosing, if I want to do the greedy part of it, then I need to compare all of the action values and pick the one that's optimal, right? So I'm comparing them. And then when I'm forming regression targets, remember I take a maximum over actions, or action values. And if I'm doing that, again, I'm comparing them. So in DQN, whenever I'm computing action values, I'm comparing them. And so it makes sense to just compute them all at the same time so that I only need one pass through the neural network. Yeah?
Why do you have this many readouts as each to a real number, presumably, rather than just one readout with a vector?
It's equivalent. I've represented it this way because it's easier to see what's going on. The idea is you have one readout for each action, but the question was, why don't you instead just have like a mapping from here to another vector that's got one element for each one of these different action values, and these are exactly equivalent. They're just different ways of describing the same thing. This is one way of describing it that makes it very clear what's going on. That you have like one readout for each one of these actions. But yes, in implementation, this is exactly equivalent to just having a linear map that maps you from the output of the network body to a vector space where each element of that vector space is one action, is indexed by an action. Yeah, that's exactly equivalent. So in DQN, you have one head of the neural network for each action, or equivalently, a mapping into action space or into a vector space of length number of actions you have that computes the actions value at that input state. Okay, so yeah, I mean, I've already said this numerous times, but what kind of action space are we restricted to if we want to use DQN? Yeah, discrete, right? I can't use this if there are infinitely many actions or a continuous collection of actions. It only works in the discrete case. Okay, yeah, so I kind of already covered this, but just to really hammer it home, why do we compute these all simultaneously rather than one by one? It's because when I'm computing these action values, it's because I want to compare them. I want to know which one's highest, and so I should just do it all at once rather than one by one. Yeah, and this maximum operation comes both in greedy action selection and in forming regression targets. So it makes sense to compute all of these at the same time, and this reduces the amount of total computation you have to do. Because otherwise you would have to do one pass through the network for each action available to you, and this is called per action DQN, and it's less efficient. Great. So how is the network architecture going to be different for DDPG? So I've already told you that DDPG is for continuous action spaces, and so you might have an idea of what this has to look like if I put that restriction in. And namely, I have to now feed in state action pairs because I can't read out into action space. Instead, I need to put the action in to begin with. So I'm going to take my state action pair, and I'm going to, and usually the way I do this is I have my state representation, I have my action, and I just concatenate these two things together as vectors. There's other ways of combining the information, but usually it's something like that. And then I'm going to feed it into my neural network body. This is, again, an MLP or a convolutional neural network or a transformer or an LSTM, doesn't really matter. And then I'm just going to have a single readout, which is just going to be a linear map from the output of the neural network body into a single number, and that's my action value estimate for that state and that action, right? So in DDPG, you feed in state action pairs into the network and have one value head which computes the value of that pair. Does anyone have any questions? Yeah.
Why does this remove? You could just
so the question was, how does this remove applicability to discrete action spaces? And you can apply this architecture for DQN. You can do the entire DQN algorithm with this architecture instead, but it's going to be less efficient. So this is applicable to discrete action spaces, but if you condition on being in a continuous action space, then you kind of have to have this architecture if you don't know any additional structure on the space that you have. So why is it okay that I can only get values for one action at a time? So in DQN, I made this big deal about like, it's like really important that we compute all of the action values at once because it massively saves on computation. Why is it fine that I only need to do one action at a time? So firstly, on a continuous action space, you can't compute all action values simultaneously. You don't have any structure on that action space or structure in your value function, you just can't do this. But more importantly, DDPG is actor-critic. And what this means is that the role of the value function now is just to provide a signal to the policy about how it needs to change. So the role of the action value function is just to evaluate and critique the policy's actions. So why is this relevant to only getting one action at a time? It essentially means that you only need the ability to say locally around any action what is better or worse. So you only need the ability to provide what we're going to see is gradient information about which action, how do I need to change this action to make it better or worse, rather than global evaluation over all actions. So that's why it's going to be fine that we're only computing action values one by one rather than all at the same time, because we only need this local information, this local learning signal. And for that, we can just feed in one action at a time. So it's this locality. And the locality comes from the fact it's actor-critic. Comes from the fact that we're now just using Q as a learning signal for our actor. All right, questions? No. Great. Okay, so we've covered how they differ in their Q network architecture. Now let's talk about policies. So how does action selection work in DQN? So DQN is an action value method, which again means that it's just going to learn a Q function and then just use this for everything. And in particular, you use your learned value function to select actions. And when you evaluate the performance of your algorithm, you use greedy action selection. So the epsilon greedy action selection that I alluded to earlier, this is what you do when you're training. And the reason you do it while you're training is because the injection of noise, so the epsilon, allows you to explore different actions that you might not normally take, so you can learn if they're better or worse than the current action you think is the best, right? That's why the epsilon's there. But then there's no reason to inject noise when you actually just want to evaluate how well the algorithm performs. So you train, and as you're training, you're interacting with the environment, and you use this epsilon greedy action selection, so you can inject noise and you can explore, but then at the end of training, you turn that randomness off, and you just do greedy action selection. You just, at all points, select the action you currently think is optimal. So the action A in state S is just the argmax of this Q function. So you just the best action. During training, you use this epsilon greedy action selection, and this allows you to explore actions off each state, right? So in DQN, we have a policy, but the policy is implicit. It is defined via my action value function rather than having some explicit representation of policy, right? So this makes it an action value method. The policy depends on or is induced by the value function. How are we going to do action selection in DDPG? So for a continuous action space, you can't do greedy action selection anymore because you in general can't compute the maximum of Q, right? There are like many different ways you can try to optimize Q, but you can't in general compute its maximum. So we're going to see today like one way of approaching the problem of dealing with continuous action spaces. I don't want you to get the impression this is the only logical thing you can do. There are many, many, many other ways you can approach the problem of continuous action spaces. DDPG is just one of the ways, all right? So, so we can't compute exactly what the maximum is going to be, so we need to take a different approach. And what's the approach taken by DDPG? Well, the approach that DDPG takes is to learn a policy that maps from states to actions. And this policy is going to be deterministic. What I mean by deterministic, it just maps directly from a state to an action rather than from a state to a distribution over actions. So a mapping from states to distributions over actions is a stochastic policy. A mapping that just takes in a state and tells you which action to perform is a deterministic policy. So we're going to learn a deterministic policy, mu s theta. So we have this new neural network now that depends on theta, or parameters I'm going to denote by this theta, that just takes in states and shoves out actions. And when we evaluate the algorithm, we act according to this policy. So I'm in a particular state, I shove that state into my neural network, my neural network spits out an action, I perform that action, and then I move on to the next state. And then I shove that state into my neural network, get an action, perform that action, and I keep going like this. And this is how I evaluate the algorithm at test time. So this is akin to the greedy action selection in DQN that I do at test time. But just like in DQN, I also want to explore my environment. So during training time, I'm going to inject noise into my policy so I can explore different actions off the states that I'm visiting. So during training, you add Gaussian noise to the policy to explore these actions. And you might also do something like clipping the Gaussian noise so that to make sure that you end up in the right action range. So if your actions have to be in close 0, close 1, have to be between 0 and 1, then your noise might shove you out, and then you just clamp back to the boundary of that. But yeah, that's just sort of an implementation detail. Another thing is, here I've said Gaussian noise. In the first implementation of DDPG and in various iterations since, different noise processes have been used to noise this action selection. So different ways have been developed for injecting noise into how you select actions. It's sort of been found that it doesn't matter that much and that Gaussian noise is very simple to do, so we usually do Gaussian noise. But yeah, older implementations use other forms of noising the policy. So the adding Gaussian noise to mu, to action selection, this is akin to the epsilon part of the epsilon greedy action selection in DQN, right? So in both of these algorithms, we have a way of action selection that we do at evaluation time, which are respectively greedy action selection and choosing according to mu. And then we have a way of choosing actions that we do during training time that we do specifically to explore the environment. And this is respectively epsilon greedy action selection for DQN and noised action selection for DDPG, where we add Gaussian noise to mu. Yeah, so this is just what it looks like. You just have some variance. The variance here is akin to the epsilon. It controls how much noise you want to inject. So sigma squared is very large, you're adding a lot of noise. Sigma squared is very small, you're adding a small amount of noise. And something you might do during training is gradually decrease the amount of noise you're injecting. So in DQN, you might gradually decrease epsilon over time. You might start with it like 50%, like just random actions half of the time, and then you decrease it down to only 1% towards the end of training. And in DDPG, you might start with sigma squared being very large, so you sample a lot of different actions, and end with it being very small, so you're only exploring local actions around the action you currently think is optimal. All right, any questions about this? Yep.
Just wondering, you said that like it doesn't matter too much what type of noise you use, but I guess there's an assumption there that small changes in your action result in small changes in the results. So like, as far as an exploration policy goes, is there not an efficiency trade-off where actually like choosing something which has much heavier tails would explore the space much efficiently?
Yeah, so the question was, given that we're using a Gaussian, is there sort of an assumption going on that we don't care about like sampling from heavy tails away from the actions we're currently choosing, and instead can like concentrate on actions very close to the one we're choosing? And you're entirely right, we are sort of making that assumption. And in fact, if you go through like the underlying mathematics, you do require sort of continuity and differentiation assumptions about the underlying environment in order for this algorithm to actually have a theoretical basis. Yeah, so we are sort of making those, and if you have an environment where you believe that like it may be that you can get really far off from the optimal action, you might choose a noising process that's more heavy-tailed. Yeah. So again, like this kind of implementation detail, once you understand why we do it and what it's there for, you can play around with it if you think you're in a particular problem domain where that assumption might not hold and you might need something different. Okay, yeah, so both DQN and DDPG use random exploration, which just means that you inject randomness into the action selection, and you don't do it in any kind of clever way. You're not saying like, I have lots of uncertainty about which action's best here, so I'm going to use more randomness. You just say at all states, epsilon level of randomness or sigma squared level of random noise injected into the policy. So your overall policy stays close to the policy you deem as optimal. So epsilon greedy is close to greedy, and the noised mu is close to mu. So you stay close to the policy you deem to be optimal, but you also explore away from that policy as well. So the staying close to the optimal policy allows you to sort of refine that strategy and get into the parts of state space where you need to gather data, you need to get that experience, while the randomness allows you to explore in that portion of state space. It allows you to try different things off that state. All right, let's get on to value function training. So we've covered what architecture they use for their Q functions, how they interact with the environment. Now we need to cover how they differ and how they train their Q function. So first of all, value learning in DQN. In DQN, you learn by fine-tuning the neural network on an L2 loss. And the way this looks like is this is going to be your loss function. So it's a loss as a function of your network parameters phi. So L here, function of your network parameters phi. And you're averaging across your mini batch of samples from the memory replay buffer. So I've sampled capital N, and N would be something like 32 or 64 or 128, not like 10,000. It would be a smaller number. You subsample N transitions from your memory replay buffer. For each one of those transitions, you form a regression target, and then you retrieve the action value off the input state, and you regress that action value towards Y. So you're trying to get Q closer to Y, and Y is your value estimate, and you're trying to bring your value function closer to that value estimate, right? That's the function of this loss. The regression targets Yi, these are formed by, again, you take the Bellman equation, you bootstrap by replacing Q with your current Q function, or your target Q function rather, and then you subsample so that you're model free, right? So if you do that operation, you end up with this here. So reward plus discount, because it's one step in the future, next state value, which is given by this, so maximum of all actions over the next state of the action value at that next state, and then you use the done signal to force the terminal, states of the terminal to have zero value, right? Yeah, and these are obtained from the Bellman optimality equation, which looks like this, right? So again, the process goes, I take this equation here, I replace the Q star with my current my target Q function. So I take this Q function here and I shove it in here. I then apply the done signal here to force terminal values to zero, and then I sample instead of taking expectation. So I get rid of this expectation and I sample the transition from the environment. That's how I form this regression target. So the reason I'm going through this in detail is because I want you to know, if you need to know how to form regression targets for some other algorithm, how do you do it? You go through this process. And that's what we're going to do. Okay, value learning in DDPG. So in lecture 2, we derived Bellman equations for basically 3 different Bellman equations. We derived a Bellman equation for the optimal action value function, which we just saw. It's this one. And then we derived Bellman equations for a deterministic policy and a stochastic policy. And in this case, we want the Bellman equation for the deterministic policy, right? That's what we're going to be using here, because we're going to try to evaluate, we're going to try and learn a value function for our current policy, for that deterministic policy we're currently pursuing. And this looks like this, right? I have my value function for my deterministic policy mu at a particular state action pair. And this is equal to, I take an expectation over all transitions off that state action pair. So the expectation is conditioned on S and A here. And I ask for all of these possible transitions, what's the reward that I get for that transition, plus discount factor, because it's one time step away. What state do I end up in, S prime? What action will I be performing off that state? Well, that's mu of S prime. That's the action I'll perform off that state that I end up in. And then what's the value of performing that action in that state, right? So again, this Q mu S prime mu S prime, this is just the value of being an S prime, and the value of being an S prime, if you're pursuing a deterministic policy, is just the value of being an S prime and doing the action that you will do in that state. This makes sense? Yeah, so we're going to learn our action value function by, again, just doing fine-tuning the neural network on the same loss, right? So we're going to fine-tune on the same loss, but now we're going to change how we form these regression targets. Yeah. So what we want to do is ask ourselves, now I want Q to learn to be Q mu, right? I want to learn the value function for the policy I'm pursuing, all right? Or rather, let's just leave it at that for now. For the policy I'm pursuing. So now I have to ask, how do I form regression targets now? So we'll just take a brief pause and just think, or if you have paper in front of you, try to write down what you think the regression targets are. I'll give you like 10 seconds for that, maybe slightly longer. Okay, does anyone fancy taking a shot? Any volunteers? So to work out what the regression target should be, we need to ask ourselves, what was the process we went through last time, and how do we replicate it here, right? So first step of the process is I do bootstrapping, right? So what does bootstrapping mean? It means replacing the Q mu that appears here with my estimate for Q mu. My estimate for Q mu is going to be my Q function. So I'm just going to replace this Q mu with the Q function, all right? And then the mu here is just going to be my policy. So the first step is to bootstrap. It's to replace this Q mu that's appearing here with my Q function. And that's bootstrapping, right? I'm forming my regression target using my current value function, right? What's the second step? Can anyone remember? Yeah, so the second thing we're going to do is we want to make the algorithm model free. We don't have access to this expectation, so instead we're going to sample. So the second thing we do is sample. So we're going to replace the expectation with yi equals, and then there's going to be an ri plus gamma q si prime mu si prime, right? So again, we're replacing this expectation with a sample. That's the second step. What's the last thing we need to do? Anyone remember? Yeah, so the final thing is just this cheap trick. We're going to include the done signal, which means just pre-multiply this by 1 minus d, and this is going to force terminal values to 0. That's the purpose of that. So behold, this is our formula. And it's pretty much exactly what I said. The one thing that we have to note is that when we bootstrap, we do it with target value functions and target policy. So the phi here is the target network parameters, which remember are just a delayed version of the network parameters, right? And the mu here, the theta minus here, is again just going to be a delayed set of parameters.
Did you make any comment on the architecture of mu? DDPG? It's just output to a kind of.
So the question was, did I talk about what the architecture of mu is, and I think I went over it very quickly. It is just a neural network that takes in states and shoves out actions. So if your action space is 4-dimensional, so say you're controlling the force on 4 joints, your action space is 4-dimensional, so you just output something that's 4-dimensional, and this is your action output. You take in states, you shove out actions, and that's the architecture of mu. Yeah. So the reason we went through that is I want you to understand how to generalize these rules I'm giving you for forming regression targets to new algorithms, right? How do you, in general, form regression targets? You do these 3 operations. You bootstrap, you include a 1 minus done signal to set terminal values to 0, and you replace expectations with samples. And this, just as a general formula, will get you very far. It's very good to just memorize these 3 steps. So yeah, we call mu s theta minus the target policy network. Why? Because it's used to form regression targets. And we call q sa phi minus the target value network. And the phi minus and the theta minus are delayed sets of parameters. The function of this is that we're trying to replicate how value iteration works. So remember, in value iteration, we're taking our current q function, we're trying to form a new one off that, and the theta minuses and the phi minuses are functioning as the delayed versions of our networks that we're trying to learn off. Great. So the only thing that's different here is how I form regression targets. It's the same loss, I just form regression targets in a different way. Before we move on to this, any questions? Great. Okay. So a brief aside. It's not super important for you to know this, but it's interesting information. So in both these cases, we're using a mean squared error loss, with the mean squared error loss being between our value function and our regression target, right? We use a mean squared error loss between these things. Why? Why this choice? So you could choose, and I've seen people do it, other losses that just the absolute error, right? So you just say it's going to be absolute value of q minus y, right? The absolute value of the difference of these things. Why do we instead choose the squared error? Why is this the common choice? What's the underlying reason for this? So recall that in both of these algorithms, to form the regression target, one of the 3 steps is to sample. It's to go from an expectation over transitions to a sample of a transition. Right? That's one of the steps. And the MSE loss has a very special property that essentially it means that essentially it counteracts the randomness introduced by sampling transitions. We're not going to go into the maths of this, but you can look this up if this interests you. But I just want to tell you the underlying reason, and then if this interests you, you should go and read about it. But the MSE loss has a particular property that other losses don't, where if you sample the transitions, then the MSE is able to sort of counteract the randomness that you introduce by sampling the transitions. So that's why we use it. Again, if you're interested, either come chat afterwards or look this up in your own time. Great. Okay. We're now going to move on to policy training. So I've covered how do I train the value network, where do my regression targets come from, how do I interact with the environment, what does my value network look like. Now, DQN doesn't train a policy, but DDPG does. And this is a new thing. It's a novel aspect of DDPG that we've got to train a policy. This is the first time that we've trained a policy, and we're going to look at one way of doing it. Again, I have to stress, DDPG is one way of dealing with continuous action spaces. It's not the only way. So this is, again, one strategy for training a policy on a continuous action space. It's not the only strategy. So in DDPG, we have our value network that computes the values of actions. And I've already told you that this is a critic. We're in an actor-critic algorithm. This Q is a critic, and its job is to provide a signal to mu about how to change its actions so they get better. So suppose that I'm not training mu, right? And I just want to choose which action to take in one state, right? So So you give me a state and say, I just want you to choose an action in this state. All right? So does anyone have any like ideas of how we might go about this? What could we do to choose this action if you just want to choose one action in one state? How would you go about doing this? Suggestions?
Big network which as an output has like 2 parameters, but there's a 2D action space. It just gives you a value for the action, and there's a it's just a network which takes in your states and produces the action. Just like a straightforward default network.
But how do you So that's sort of like what we're trying to do, right? We're trying to get a network that maps from states to actions. But the question is if I just have one state, so I give you Q, right? I give you a action value function that's able to tell you the value of any action. And I give you a state, and I say, I need you to choose which action to take in this state, right? And we don't have anything else. How would you go about doing this? Okay, so we're getting closer, right? So what we want to do is optimize over A. Right, that's the obvious answer, like first pass, that you want to find the action that maximizes Q, right? You want to find the action that has the highest value. So you want to optimize A. Okay, how are we going to optimize A? There's many ways that one can, this is a function of A. There's many ways that one can optimize a function of A. What could we do? Suggestions? Gradient descent. Well, it's going to be gradient ascent, right? Oh, right, so ideally, we want to compute this argmax. Ideally, we want to choose the action that maximizes Q, right? But we are in machine learning, and so whenever we want to maximize anything, we're just going to do gradient descent, right? This is the only way we know how to do anything. So we want to compute this argmax. How are we going to optimize it? And so one option is to use gradient ascent, so to iteratively move the action in the direction of increasing value. So I start with some random action, and then I keep updating this action to have a higher and higher value, right? And so I keep applying this rule. My action choice in state S is just going to be my previous action choice plus some learning rate of the gradient of my Q function at that previous action choice, right? This is just a mathematical expression to say do gradient descent on Q. Right? But of course, we can't like individually maintain for every single state. We can't individually maintain what action to take in that state. This isn't possible because the state space is either astronomically large or it's infinite, right? So we can't individually maintain which action to take in which state. So instead, what we need to do is do what Carl suggested, and instead define a mapping from states to actions, and then optimize that mapping by gradient descent. So instead, we have this parametric mapping that takes in states and spits out actions, and this is our policy, mu s theta, right? And to train the policy, we're just going to do gradient ascent on the policy objective, which is just the value function, right? So all we're going to do is we're just going to take our function that maps from states to actions, and we're going to keep adjusting that function so that it spits out actions that have higher and higher, that do ascent on the Q function, that do that increase the action values via this gradient ascent. So this is what the policy objective looks like. I average over a mini batch of states. So again, I have my big memory replay buffer, 1 million transitions, subsample 32 of them. That 32 is my N. I average over those 32 states that I sampled from my memory replay buffer. And then at each one of those states, I ask, what action does my policy take in that state, right? And then I'm just going to do gradient ascent on that action choice, right? So I'm just going to adjust theta. So this is a function of theta, j theta. I'm just going to adjust theta so that the value that my value function assigns to that action goes up, right? It's a very simple concept in the end. It's just do gradient descent on Q and like specifically learn a parametric mapping and then do gradient ascent via this parametric mapping. Yeah, so if you want like a technical term for what's going on here, this is what we call amortized optimization. So the optimization comes from the fact that I'm doing gradient ascent on Q. The amortized comes from the fact that I have this mapping here, that I have this parametric mapping between states and actions. So because I can't individually maintain an action value for an action to take in every single state, instead I learn a mapping and I optimize this mapping, and this is going to allow me to, one, like do things in finite time, and two, generalize, right? So I want to be able to know which action to take in a state that I've never seen before, and this mapping is going to allow me to do that in a way that just doing gradient descent individually is not. Yeah, okay, questions now? Yes.
Until now, there are two places where you had to assume locality that you don't have in DQN, right?
So
one is when you use exploration on Gaussian, and then
yeah.
here for conversion.
So so there's no, we aren't really making, so the question was about what assumptions of locality am I making? And really this is just like a reasonable strategy, and that I have like no guarantee of convergence at all. And as usual in ML, like I don't really have guarantees of convergence, and I'm generally in practical setting I'm not interested in guarantees of convergence. I think my next slide might answer the rest of your question. So maybe ask again at the end of the next slide. Does anyone have any more questions about this specifically? Will? No? Okay. Great. So again, another aside, by which I mean you don't have to pay attention to this, but it would be nice if you did. So DDPG is performing this gradient ascent on action values. And the way I introduced this was just like trying to motivate why intuitively this makes sense to do. You have a thing that you want to optimize. How do we optimize things? We do gradient ascent. Very simple and logical. But it's not just like made up. I haven't just pulled it out of nowhere. There is a reason for doing this. And that reason is the deterministic policy gradient theorem. So again, this is a term that I'm not going to explore, but if you're interested, you should go and read up on. But essentially, the deterministic policy gradient theorem tells us that under some conditions, and some of those conditions are things like continuity of the environment, and yeah, differentiability of the environment, ascent on action values is equivalent to doing ascent on expected return. So the expected return is just this. It's if I always choose my action according to my policy, then what's the return I'm going to get in expectation over all the possible transitions I could experience, right? And remember, this is the thing that we like actually care about, right? Like at the end of the day, at the end of everything, the thing we actually care about is to choose a policy which gets us a high return, right? That's the thing we really care about. And it turns out that under certain conditions, doing ascent on action values is, in fact, equivalent to doing ascent on this expected return. Yeah.
This is not obvious, since action is the only thing we can do to get a reward given a state. So it's the only thing we can optimize, and of course increase the return.
Yeah. So the question was, is it obvious that these two things are equivalent? Because if your action's the only thing you have control over, so like obviously if you increase action values, you should get a high return. And it is maybe quite obvious that if you increase action values, then you should get a high return. But the claim is not that. The claim is not that. The claim is something stronger. So the stronger claim that I'm making is that, in fact, you're not just increasing this. So it's not that doing ascent on action values increases return. It's that you are doing gradient ascent on this return, right? This is a stronger claim. It's a claim about the equivalence of two different gradients. You have gradient of action values, you have gradient of return, and it turns out that under certain special conditions, these two things are exactly equivalent to one another. They're just different ways of computing the same gradient. And you can't compute this gradient, but you can compute the other one, so you compute the other one and you use that. Yeah. So it's a slightly stronger claim than just return will go up if you do gradient ascent on action values. Yeah. So again, this sort of justifies the entire approach, right? Like this is the thing we really care about, and what I've shown you as a method is like secretly just increasing this thing. Yeah.
Killer applications of DQN, the initial ones were with the board games, CSGO and such,
Yeah.
which are very non-local. So other practical examples where DDPG does find a very non-local path, like doing some very different things.
I don't know if, I mean, so neural networks can definitely, so the question was, is DDPG able to find non-local paths where it like, I'm guessing you mean like rapidly switches which action to take when you change the state a small amount? And the answer is, I mean, because you're using a neural network, provided your nonlinearities are all continuous, then your mapping is continuous. And so in the sense that you can never learn a discontinuous mapping, then no, you cannot learn a discontinuous solution using this. But you can, with a neural network, arrive at very sharp changes that aren't actual discontinuities, but do rapidly change the state. And I'm sure that in certain environments, DDPG will learn to have very sharp changes of action in across states. But I can't speak to like how often that happens or how good it is at doing that. Right? Okay, so we're almost done. Yeah, we're almost done. The next thing we need to cover is how the target parameter updates work. This is like less important than all the other parts, but it is part of the algorithm, so we'll cover it. So target parameter updates in DQN, remember this is motivated by having an old Q function that you're learning off in value iteration. And the way it works is you synchronize your target Q function every 1,000 gradient steps. You just synchronize it. And what does synchronization mean? It means you load the current network parameters into the target network parameters every 1,000 steps. And so between synchronizations, regression targets don't change, right? So during that period of time, phi is changing. Phi is being updated. Phi is being fine-tuned, right? But phi minus is static, right? Between synchronizations, phi minus is static. And this is really good for the algorithm because it provides stability, right? It sort of fixes the learning problem for 1,000 steps, and then you change it when you synchronize to a new learning problem. But during that time, the learning problem is static. You're always forming the same regression targets. You're always trying to learn the same input-output mapping. And this provides a lot of stability to the algorithm and helps it not do things like oscillations and divergence of Q values. And generally, it's like a very important step in terms of practically getting this to work. So between synchronizations, the phi minus doesn't change, so the target value function doesn't change, so the regression targets don't change. So this provides a lot of stability, but it can also slow down convergence because regression targets get out of date between synchronizations. So as I'm changing phi, phi minus gets gradually more and more out of date, and so my regression targets, my convergence slows down a bit. So the question is there a way that we can have the best of both worlds, where we have a delayed set of parameters, phi minus, that provide stability, but not let phi minus get so out of date and have such a long period where it's not changing? And the answer is yes, there's another way you can do it that provides the best of both worlds. And the way we do it in DDPG is to move the target value function and target policy closer to the normal value function and normal policy every gradient step. And what do I mean by closer? I mean closer in parameter space. So the specific method I'm using is something called Polyak averaging. And how it works is that in synchronization, I move all the way. I say, here's my current parameters, here's my old target network parameters, here's my current network parameters. I'm just going to move them the whole way. in Polyak averaging, I say they're some distance apart, and I'm just going to move my target network parameters closer. Right? So I'm just going to move it a little bit closer. What do I mean by move it a little bit closer? I do this operation. So rho here is a constant, and to give you an idea of order of magnitude, typically rho is set to 0.999. And what this means is that I am moving 0.001 proportion of the distance between my target network parameters and my current network parameters. So each update I do, I say there's some distance between them, and I'm going to find this distance, and then I'm going to move 0.001 times that distance towards. So 0.1% of the distance I'm going to cover towards the network parameters that I actually have. And because these are delayed, because they lag behind, they're constantly following the actual network parameters, this provides the same stability that you get in DDPG, but because they gradually follow, you don't get so out of date. And this turns out to be a better way of doing things for DDPG. So yeah, like a normal number for rho to B would be 0.995. That's 0.5% every step of the distance that you cover. So the target networks now are smooth, delayed versions of the normal networks. So before they were just lagged, now they're smoothed as well. This does a sort of smoothing operation. You might know it as exponential moving average, and this sort of helps the not to get so out of date so quickly. Okay, let's summarize DDPG. So again, like big algorithm on the screen. Let's have a look at the whole thing. We have an interaction step, then a value function or critic update step, then a policy or actor update step, then a target function update step, and we're going to loop this whole thing. Right? So again, just a big loop outside this. I'm going to do each of these 4 steps in turn and then loop the whole thing. So in the interaction step, again, I'm going to do the same kind of thing as DQN does, where I interact with the environment for 10 steps using a noisy policy. Right? And remember, the noisy policy is equivalent or does the same job as the epsilon greedy policy in DQN. It's the same function being played. For each one of these transitions I experience, I load it into my memory replay buffer that contains like 1 million experiences. Then I need to update my value function. How am I going to do this? Well, I'm going to subsample 32 transitions from the memory replay buffer. For each one of those transitions, I'm going to form a regression target. Right? And remember, the way we got this regression target was we bootstrapped using our target action value function, our target policy. So we bootstrap using them. We add in this 1 minus d, which sets the value of terminal states to 0. And then we remove the expectation. So that's why we have i's here, because this is what we actually experienced in our transition. And that's how you form these regression targets in general. Right? You just do these steps. And then we fine-tune Q on this mean squared error loss, doing one update step, so 1 step towards the regression targets. In the policy or actor update step, we're going to update the parameters of our policy, mu s theta, by fine-tuning on the average value objective, which is just to do gradient ascent on action values, right? So when it comes to training the policy, we're just going to do gradient ascent on action values. And then finally, the last step is we're going to update the target functions. So this is the target policy and the target action value function. We're just going to update these via Polyak averaging. So just obeying this rule here, where we move a tiny bit closer to the true network parameters, doing this exponential moving average style update. And then we loop the whole thing. Yeah, let's briefly pause for questions. Otherwise, final slide is next. Okay, so this is a big summary of the similarities and differences between DQN. So the value network architecture, DQN, maps from states to action values of every action off that state. In DDPG, you put in a state action pair, you get a single action value out. For exploration, DQN uses epsilon greedy. For DDPG, we use a noise corrupted version of the policy network. When we form regression targets, in DQN, we're going to form the regression target by taking a maximum of next state value. And in DDPG, we're going to form the regression target using the target policy, right, by just plugging that into our Q function. To train the policy network, DDPG doesn't have one. That's not a thing. DQN doesn't have one. DDPG does gradient ascent on average action value. And for target network parameter updates, DQN does synchronization every 1,000 steps or so, and DDPG does polyc averaging after every update step. Great. Thank you all very much for listening.